Swayam Prabha. Digital India. Educated India.
So we left off here, right, before the break. So we are talking about optimal action value functions and how you can recover a optimal policy from that, given I tell you what the optimal value function is. Right? Make sense? Everybody on board? So next, what do we have to do? We have to figure out a way of learning what that optimal value function is. Correct? Right? So let's start by looking at what's called Q-learning. Right? So Q-learning is a completely incremental learning algorithm. Doesn't require you to know anything about the system dynamics. All the Q-learning expects is that you have experience of this form. You remember we talked about this, right? You start from a state S, you take an action A, you get RT plus 1, you go to ST plus 1, and so on and so forth. You remember this? This experience that we're talking about? Great. Right, so all you need is this kind of experience. So this is what we mean by interaction with the system. And other thing is it's also fully incremental in the sense that every time you take an action and go to a next state, you do something to change your value function. Right? So that's basically what we're doing, right? So we'll look at what is called one-step Q-learning. I'm not going to talk about the other versions of Q-learning today, but look at something simple like one-step Q-learning. And this is the update equation, okay? How did we come to that update equation? So I'll take a few steps slowly, but let us refresh your memory. So what is Q star? Q star is that expression, right? It's an expectation of RT plus 1 plus gamma max over A prime Q star ST plus 1 comma A prime. This is what we had earlier, right? In one of the previous slides, if you, right? So this is what we had. Right, you remember that? So we fix an action A and then we behave optimally thereafter. So that is where the max comes. Among all possible actions I could take, I pick the best possible action according to Q star. Okay. So this is my optimality equation for Q star, and that basically becomes this. So the key point to note here is that Q star is nothing but an average. Right? Q star is nothing but an average. So we are talking about an expectation. An expectation, all you need to remember is the expectation is nothing but an average. Right? Great. So let's do a slight detour now. Let us talk about how we estimate expectations. Right? Suppose I want to find out the expectation of some variable x. So what do? I take a lot of samples xi, sum them up and take the average, right? That gives me the expectation. So this is something that all of you are familiar with, right? The first expression that we have there, everyone is familiar with that expression, right? Let us now try to do this in a slightly different way. Let us say xn bar be the average of the first n samples I have taken, right? I'm taking n samples. I'll say xn bar is average of the first n samples, okay? Now I go and take one more sample. This is where the incremental part comes in. I already have something. Now I'm taking one more sample. That is incrementally I'm taking one more sample, and that sample we'll call it as xn plus 1. Okay. Now I want to compute xn plus 1 bar or x bar n plus 1, right? I have x bar n. I want to compute x bar n plus 1, right? I already have x bar n. I also have xn plus 1, right? Now what will be the total of the first n plus 1 samples? That's what we have to find out, right? I have to first, when I want to find out x bar n plus 1, I have to find out the total of n plus 1 samples and divide by n plus 1, right? So what will be the total of the n plus 1 samples? It will be n into xn, x bar n, right? N into x bar n, because x bar n I obtained by adding up the first n samples. So n into x bar n plus the n plus 1 sample divided by n plus 1. Correct? This is my new average. Make sense? Now I am going to do some arithmetic here. So I am going to add and subtract x bar n. Right? Now I can write it as, so this two I can take together and write it as n plus 1 into x bar n, and these I can write it as xn plus 1 minus x bar n. Okay? Then I can take the n plus 1 inside. So this will become xn bar, x bar n, and this will become 1 by n plus 1 into xn plus 1 minus x bar n, right? So this part is clear, right? I just taken that n plus 1 inside. Okay. Now I can denote this by some constant. I'll call it as alpha. Okay. So I'll have xn bar. Is it okay if I say xn bar or x bar n? You guys know what I'm talking about, right? Okay. So I have x bar n plus alpha times xn plus 1 minus x bar n, right? So the general form for this, you can see, is that my new estimate of the average, which is x bar n plus 1, is equal to the old estimate, which is x bar n, plus some alpha times the new sample minus the old estimate. Right? My new sample is xn plus 1, my old estimate is x bar n. Okay? So this is essentially a very simple way of taking average in an incremental fashion. Right? You can think of this as an incremental averaging rule, or it's called the stochastic averaging rule. Right? So stochastic averaging rule is this, right? So why is this of interest to us? So if you think about it, right, this is the Q learning update rule I wrote, right? So what does Q learning do? It computes an expectation. Q star is an expectation, right? So if you think of this quantity in the circle there, that is just my new sample, right? Right. So I should probably put the expectation back on the slide. See, this is the quantity I'm taking the expectation of, right? This is the quantity I am taking the expectation of, right? See, I had put E of x, right, earlier. So this is my x, right? So my x n plus 1, right? This is my n plus 1 sample I am taking for x, right? And my old estimate, instead of x bar n plus 1, is my q hat, right? So that's my old estimate. So my new estimate is equal to the old estimate plus alpha times the new sample minus the old estimate. So it's just nothing but an averaging rule, like stochastic averaging rule for computing that expectation that we had earlier, right? That's all Q learning does, right? All you need to now do is have some way of generating new samples, okay? Right, so now we are back to the original slide, and so this now you can see is nothing but just a stochastic averaging rule. But interestingly, if you notice, it also has the t plus 1 minus t form, right? It has a t plus 1 minus t. So what did we talk about earlier, that they had a t plus 1 minus t? The temporal difference, right? It turns out that it's also a temporal difference learning rule, because we are looking at estimates from t plus 1 and using that to change the estimates at time t. So it's a temporal difference learning rule as well, right? Right. So I mean, there are many ways in which you can derive the Q learning rule. I just showed you the averaging way of doing it, right? So you can actually derive it using differential equations, right? So you can derive it using the temporal difference idea. So many ways in which you can derive the Q learning rule. But just remember that at the end of it, it's nothing. You're just computing averages. There's nothing very complex about the learning rule. Fine. So people understand what Q learning is? You better. You're going to do it in the lab. You're not going to do it in the lab. I mean, you're going to do something simpler than this, but you better have some idea what it is, right? So there's also a version of this Q learning that is called SARSA, right? We'll come to that in a minute. So it looks very similar to the Q learning rule. What is the difference here from the Q learning rule that you can see? Yeah, the Q learning rule, I did a max over A, right, and found the best action that you could take here. Okay. In SARSA, I just plug in whatever action you really took, right? So remember, this is what we are talking about, right? ST, AT, RT plus 1, ST plus 1, AT plus 1, and so on and so forth. When I plug in AT plus 1 there, I am actually plugging in the action that you really took, okay? Not an action that is the best possible, right? You just plug in the action that you really took there, right? So why am I doing that? If you remember, we talked about another action value for Q pi, right? Not Q star, Q pi. Look at the expectation there. So what does the expectation there tell you? It is RT plus 1 plus gamma times Q pi of ST plus 1, AT plus 1, right? So this is nothing but a stochastic averaging rule for q pi, right? This is a stochastic averaging rule for q star, right? This is a stochastic averaging rule for q pi, right? But the trick here is, at every point of time, we find out what is the value of q pi, or rather make some estimate for the value of q pi, but then I change pi, right? I look at the current q pi, and then I try to come up with a new pi dash that is better than the current pi, and I keep doing this all the time, right? So the way I do this is very simple. So far, I have not told you how you are generating these samples, right? Because when you are trying to learn q star, there is no fixed pi, right? So I have not told you how you are generating the samples. But in trying to do SARSA, it looks like you want a fixed pi, right? Because I want to know what AT plus 1 is, so I need to have a fixed pi, right? So what I do is, I pick a pi that is greedy with respect to my q hat. So whenever I come to a new state, the action I pick will be the one that gives me the max over my q hat, right? I am just being greedy with respect to q hat. So as I keep changing my q hat values, I keep changing my policy also, okay? And there is a slightly involved proof that will tell you that this will actually give you the optimal policy. But what do we know? We do know that for both q learning and SARSA, convergence to pi star is guaranteed, right? As long as all state action pairs are selected infinite number of times, right? And eventually, you only pick according to the greedy policy, which is picking according to max over q hat, right? So as long as you are picking according to the greedy policy, eventually, and all state action pairs are visited an infinite number of times, then you are guaranteed to converge to both q star and pi star, okay? In either q learning or SARSA, okay? Now to come back, let's see why is it called SARSA? Because in q learning, you use the state, action, reward, and next state, right? That's all you need for making a q learning update, right? You don't care what happens after that, right? But in SARSA, you need the state, the action, the reward, the next state, and the next action. So that is state, action, reward, next state, next action. So that's why it's called SARSA, right? Luckily, they didn't name q learning as SARS, and okay, fine. So, but there is still a little tricky thing here, right? So I said that at every point of time, you select the action that looks the best according to q hat, right? And when you are doing SARSA, right? In q learning, in fact, it turns out you can select whatever action you want. It doesn't matter, because the next action you select doesn't figure in your update rule. So q learning, you can actually behave randomly and still find q star. It's an amazing thing about q learning. But let's say you don't, right? Let's say you always behave greedily. But the main problem is, so if you always behave greedily with respect to the current value function, you will not be able to visit all the state action pairs, right? You will start focusing only on a small set of the state action pairs. And here is an example of that, right? So this is the number of episodes you have learned, right? And if I am picking only greedily, so I converge to something that is suboptimal. While if I am doing some kind of trial and error learning, right? If I am doing some kind of exploration, I actually get better and better at what I want to do, right? So this is a very specific form of exploration that we picked here. So I'll explain that in the next slide, right? So people see what is happening when I'm playing greedily, right? When I'm actually picking actions greedily, I might not visit all possible state action pairs, right? Let's say you play tic-tac-toe, right? There is something that gives you a 0.8 chance of winning, right? Some action that you can take that gives you a 0.8 chance of winning, and some other action that you can take that gives you a 0.9 chance of winning, right? So you start off with saying that all actions have 0 chance of winning because you don't know anything about it, right? And then you pick one action, the 0.8 action, and you win, right? You come back again. Now you want to be greedy with respect to your current estimates. So what do you know? Action 1 gives you 0.8 or 1 because you picked it the first time and you won, right? Action 1 gives you a win with probability 1, and action 2 gives you a win with probability 0. No brainer. I'll pick action 1. right? Let's say you lose, right? What's the probability of winning from action 1 now? 0.5. I'm taking the average. It was first time I won, so it's 1. Next time I lost, so it's a 0.5. What's the probability of winning from action 2? 0. That's where I started off, right? Now, what will I pick again? Action 1. Right? So, I will be stuck doing action 1, even though action 2 has a probability of winning of 0.9. So, if I had tried action 2 a few times, I would have figured that out, right? But since I am not exploring, I am being greedy, I can get potentially stuck in something that is suboptimal, right? And of course, if I had by random picked action 2 at the first game, I might actually get stuck on action 2, which is a good thing because that's one that is the best action. So, we don't know, right? So, I am being greedy, so I can't guarantee that you will find the optimal solution. That's exactly what happens here. So, these curves are drawn as an average over 500 times playing, right? So, when I do this over 500 iterations, so on an average, I am going to converge to something that is poor. Okay. So, this is one of the things that we would want you to run. So, there is this parameter called epsilon. I'll explain what it is. So, in the labs in the afternoon, you will run experiments just by varying epsilon, right? You don't have to write code. How about that? You just have to go and change the value of epsilon in a text box, okay? And then see what happens with the curves. But then after every change you make, you will have to explain what you are seeing. That is the hard part, right? So, you are going to play with your hands, right? Change some parameters around, you will see some new results coming on the screen, and the goal here now is to explain what is it that you are seeing in those results, rather than get bogged down in writing code. Okay, the minimal like 1 or 2 lines of code that you have to write. Right? So, the simplest form of exploration that we will look at is what is called the epsilon greedy approach. Right? So, the idea here is very simple. Right? Like I said, it's simplest. Right? So, you pick the greedy action, right? Almost always. So, we call it with probability 1 minus epsilon. Right? And then you pick some random action. Don't worry about what the value is. Just pick it anyway with some probability epsilon. Right? Epsilon is usually some small number, say 0.1 or 0.01 or something like that. So, when I say epsilon is 0.1, what does it mean? 9 times out of 10, I will always pick the greedy action. But the 10th time, I will pick some action at random. So, let us go back to our example of A1 and A2. So, I will always be picking A1, right? But 10th time, I will pick A2. Now, A2 I might actually win or lose, but then given enough time, right, I would have picked A2 sufficiently so that I know that with probability of winning from A2 is 0.9, at which point I will switch from A1 to A2, right. So, it is a very, very simple thing. It does not guarantee anything that is optimal in terms of how quickly you will learn, but it does guarantee that you will eventually learn the optimal policy. Okay. So, that is what epsilon greedy does. So, what does epsilon greedy do? With some small noise probability epsilon, it will pick a random action. With probability 1 minus epsilon, it will always pick the greedy action. Okay. So, what do we mean by greedy action here? It is action that is greedy with respect to your current estimate for Q star. You do not know the true Q star. If you know the true Q star, you can be greedy all the time. If you know the true Q star, you do not have to explore. Okay, you can be greedy all the time. That is what we put in that earlier slide, right? Why you need to learn Q star? Because if you know the Q star, you can be greedy and you will get the optimal policy. Because we don't know the true Q star, so whatever is your current Q star, you be greedy with respect to that. So, that is what the Q hat is, right? So, you be greedy with respect to Q hat with probability 1 minus epsilon, and then you pick a random action with probability epsilon. More complex exploration strategies are possible. In fact, it is a very, very active area of research. Lot of work is happening in this, trying to find out what is the best way to do exploration, right? But even many of the more modern deep learning methods, even the Atari games and other things that we spoke about, actually use epsilon greedy as the exploration. So, it's still a very useful practical algorithm. It's not something that is that just so that you can run simple experiments with it. People actually use it in practical solutions, right? So, here is an example between what happens when you do Q learning and what happens when you do SARSA. Okay. So, here is a simple domain. So, we call it the cliff world. Okay. So, you have to start from the state S, you have to reach the goal G, right? And every step you take gives you a reward of -1. except if you fall off the cliff. If you fall off the cliff, you get a reward of minus 100. And then you go back to the start state, and then again you have to start from there and try and reach the goal. Okay? So now what is the optimal way of behaving here? It is that, right? Literally hug the cliff, walk on the edge of the cliff so that you reach there as quickly as possible, right? But then, while I'm learning, right, so we just saw that I need to have some kind of epsilon greedy exploration or something. Let us say I have an epsilon of 0.1. That means with some probability 0.1, I take a random action, right? So now I have the 4 actions, right? North, south, east, west, right? And if I'm walking here, with some probability I take a random action, so that random action could be south, right? So I have a probability, let's say 0.1 probability of exploring, and 1/4 of that 0.1 probability I have is of falling off the cliff. What is 1/4 of 0.1? Huh? 0.025, right? But then I have a probability of 0.025 of falling off the cliff here. I have a probability of 0.025 of falling off the cliff here, 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 here. It's not just 0.025. It's a much higher probability than that, because I could fall off the cliff anywhere. Right? You have to add up the probability of all those events. Right? So the actual value of that policy will be very low if I'm going to continue to explore. If I'm always going to say that I'm going to do epsilon greedy, right? I don't want to learn the optimal path. I would like to go far away from the cliff, as far away from the cliff as safely possible, and then take what I call the safe path here. Right? So Q learning, since it doesn't worry about what is the next action you take, it always assumes that you are going to behave optimally because it's taking the max, right? Q learning will converge to this optimal path, while SARSA, because it looks at what was AT plus 1, doesn't do the max, right? It looks at what was the actual action that was taken, right? So whenever you fall off the cliff, SARSA knows you fell off the cliff. Well, Q learning just very, optimistically assumes, okay, he might have fallen off the cliff now, I don't care. Next time he comes here, he will behave optimally, right? So it's going to assume that this is the action you take, right? When you do the Q learning update, right? Whenever you jump off the cliff, SARSA is going to say, oops, he jumped off the cliff, right? And then if you look at the overall performance that's going to happen, so Q learning, even though it has learnt the optimal path, right? If you look at the total reward that you're going to get in Q learning, it's going to be much lesser than what SARSA manages, because it's taken the safer path, right? So if you're going to continue exploring, right? If you're never going to stop, you're always going to be epsilon greedy in your behavior, even after you figure out what the best policy is, then you should use SARSA, because it will give you a safer policy. Right? And Q learning gives you something that is more. So why would you not want to stop exploring? So you might want to continue exploring mainly because the worlds that you are going to work in, right, might be very, very large. Take the Atari games, right? I'm talking about all the pixels on the screen and stuff like that. Right? It's almost impossible for you to visit every state often enough. Right? It's good to have some kind of exploration going all the time. Right? It's going to be tricky, and other circumstances, things might change a little bit. So once I have figured out what I learn an optimal policy in this world, and then I freeze it, right? And then somebody moves the chair over. Right? Now I can't use the same policy because the chair is blocking the way. And if I'm not learning anymore, if I'm not doing the exploration anymore, I wouldn't know how to solve the problem. So I would like to keep exploring and things like that. So sometimes SARSA makes it easier, right? But then on the other hand, Q learning in some sense is easier to implement, as we will see later. So many of the modern deep RL methods still stick with Q learning, while some use other forms of learning called actor critic, which we are not going to cover today. Don't worry about that. So Q learning is more popular now than SARSA is, right? So, but there are pros and cons of both. Okay. So, and there are many solution methods. We have not talked about most of them. We basically talked about Q learning and SARSA. I introduced what TD is, right? As a whole class of methods where you directly search for policies without value functions, right? And then there's a whole class of methods where you don't just work with interactions, but you assume you know the world. Right, and you use a model of the world in order to make your learning more efficient, right? So in some sense, this is the end of part 1. We ended a little earlier, and so we'll go to part 2 now. But any questions so far? So basically, we looked at Q learning and SARSA and epsilon greedy. These are the 3 things that you need to take away from so far, part 1. Okay, great. So let's look at this question of what happens when I'm going to act in very large state spaces, right? So far, I've been talking about a function, right, Q, right? I talked about Q, but I didn't tell you how you will store the Q function, right? How will you normally you think you'll store the Q function? For every state action, you'll have one entry, right? That's what you probably were thinking, like it's like a table. For every state, how will you store a normal function, right? You store it as an array, right? In C, let's say, you're writing something in C, you'll store something like an array, right? For every input value, you'll have some output. So that output you'll store in an array. That's called a table, right? It's something like a table. But then these kinds of tabular approaches are not really very memory efficient when you start talking about very, very large state spaces. Especially if I'm talking about continuous states, how will I even store a table? So what will you do in a continuous case? I already showed one example, right? I said this is the world in which a robot is moving around. So you discretize it. If I give you a continuous variable, you can say, okay, 0 to 0.1 is 1, 0.1 to 0.2 is 2, and so on and so forth. Then I can do some kind of discretization, and I can still put it in a table, right? But the main issue here is what I call the data sparsity issue. Right? Main issue is the data sparsity issue. So what do we mean by that? So remember that the Q functions are averages, right? So how do I find the expectation for the Q value? I take some samples and I take an average, right? Now if I'm going to store every QSA as a separate entry in my table, so for every entry in the table, I need to take a lot of samples so that I can take the average. Correct? So remember the grid world that we had earlier. It's too far back. Let me see. Right. So we had a grid like this. Right. We had a grid like this. So let us extend this indefinitely. Okay. Let's say that. Okay, I have a large grid. Okay. Now, if you look at the state here, right, and you look at the state here, right, their values are going to look very, very similar, right. So remember, my goal is somewhere out there, right. So the values of these two states are going to look very, very similar. So if I'm going to want to estimate the expectations here, I can actually use the expectations here also. I don't have to learn something completely independent, right? The same samples that I use for estimating the expectation here, I can probably have the same expectations here, right? So instead of trying to generate more and more samples for every state action pair, I can look at states that are similar or actions that are similar and try to generalize their values across the board, right? This just goes back to what you are learning in regression. You guys did regression? Right? So this is essentially what you are doing in regression, right? So things that look similar, you want them to have the similar outputs, right? So we need methods that can generalize experience gained over a limited subset of the state space to the entire state space, right? So what do? We use a parameterized representation, right? Just like that, right? You have a weights, you can have input coming into the network, you have all these neural network weights, and then it outspits a value, right? Or you have inputs coming to a linear regression system, you have weights and coefficients and all that, out it will spit a value, right? So you can use this kind of parameterized representations, right? So you can use parameterized representations for value functions, you can use parameterized representations for policies, you can use parameterized representations for models, whatever is it that you want. And today we will only talk about parameterized representations for value functions because we only looked at value functions so far, okay? Still with me? Okay. So what do we mean by a parameterized representation? Let me see. Do I have it anywhere? So what I mean by a parameterized representation is that, okay, So I am going to have my q hat, right? I have my q hat st comma at. I am going to say that this is going to be given by some function that takes st and at as the input and uses some w as the parameters. It could be a neural network, right? I am going to feed s and a to the neural network, and w is all the weights in the neural network. It's going to compute that and spit out my q hat, right? Make sense? Right, so that's basically what I'm doing with my parameterized representations. And remember, what am I trying to approximate with my q hat here? I'm trying to approximate q star, right? That's what I'm doing in q learning. What I really want is q star, right? So this is what I do in my least squares fit. This is essentially what you were doing in your regression earlier, right? Does this expression look familiar? Right, so I have some parameters wt, which is my weights. I'm not sure what were the symbols that you used earlier for regression, right? And right, so my target is q star, my current output is q hat. I take the squared error, I take the gradient of the squared error with respect to the weights, and then move in the direction opposite to that gradient and update my weights, right? What is the problem in using the least squares estimates for q star? Is there a problem? Can I just do regression like whatever you have learned so far? The biggest problem is I don't know q star, right? I don't know what q star is. So instead of knowing what q star is, I basically use whatever we did in the TD learning. I basically look at one time step down and use that for my q star, right? Which is essentially RT plus 1 plus gamma max over A q hat st plus 1 comma A. So what does this resemble? This whole thing is what you had as your update rule. This is called the TD error, right? So basically you take the square of the TD error, now take the gradient with respect to the square of the TD error, right? And then you do the update. So essentially what happens when you are doing this is that you are trying to approximate the least squares update for q star, right? But instead of using q star, I am going to use the TD error. This is the most complicated thing that we will do now, but that's it. I mean, if you understand what is happening here, you know what all deep learning is all about. Any questions on this? Okay. So I'll show you one specific example of this. So we'll look at what we call linear Q updates, right, or linear Q learning. So I'm going to say my Q hat is given by exactly this, right? So linear, right? So linear means the weights have to appear as linear things, right? I can't have any cross combinations of the weights, right? So I'm going to look at phi, which is phi is my feature matrix. So I'm going to look at phi of s comma a, right? So phi transpose cross w. That's basically taking the inner product, right? So that makes sense, right? This is essentially like saying. So that's basically equal to saying wt1 times phi 1 of st comma at plus wt2 times so on and so forth, right? Sorry? So phi is a way I'm going to encode my states and actions. So for example, if I do the grid world, right? Phi 1 could be the x coordinate, phi 2 will be the y coordinate. So make sense? So phi would be some way of representing this, right? So if I'm going to just say, okay, this is state 3, right? So I'm not going to give it x and y coordinates, then phi will just be 3. Just a data representation for what your state and actions will be, okay? And yeah, so going back to what we did with, let's say the cycle case, right? So I was actually describing to you the cycle thing as, okay, how fast you are moving, what angle you are tilting at, and so on and so forth, right? All of those will be phi. So how fast you are moving could be phi 1. What angle you are tilting at could be phi 2, right? How heavy you are could be phi 3. So there are different things that make kind of make up your state space, and all of that go into the phi. Okay. So the cleverness here in getting all this parameterized representation to work is finding the right phi. Okay, if you find the right phi, just linear function also will work, right? So now what you do is you take the TD error, which is this expression, right, and try to find the gradient of the square of the TD error, and what will that be? So if you think about it, so I am only looking at q hat, right? So this I am taking as the target, so I will not touch the target, so I will leave the target as it is. This is the target, I will leave it as it is, right? And then, so first thing would be 2 times this, so I will basically get my delta t back, and I will take the gradient of q hat, which is basically phi transpose wt, so I will basically end up getting just phi. I take the derivative of this with respect to w, it's only phi, right? So the derivative of this with respect to w is just phi, so I'll get that, right? And since it's minus here, so I'll get a minus, so it's minus delta t phi stat, right? So my overall update rule is, so then wt plus 1 equal to wt plus half alpha delta t phi of stat. This is very simple gradient descent rule, right? No need to do backprop or anything, just one layer here, okay? So unfortunately we don't have great convergence results for linear Q-learning. So we know that linear this update, this kind of a linear update will converge to the root mean square error minimizer, right? It will converge to those values of w that gives me the least root mean square, provided I don't change my policy pi. Provided I have a fixed pi and I'm just generating samples, right? That means no max. Okay, if I don't do that, then it will converge to q pi, right? But no such results for Q-learning. And once I start putting in the max here, I have no guarantees of convergence, right? So, and if you use anything other than linear parameterization, but we have no results at all for convergence, no theoretical results. But theory be damned, because deep RL works very well. So you have the old examples like TD Gammon and all these Atari games, AlphaGo, all the examples I spoke to you about, recent success stories of RL. All of them use parameterized representations, right? And none of them are supposed to work according to theory, but they work anyway. So basically, the theory has a lot of catching up to do, right? So deep RL gives you this significant success stories. And so we'll talk a little bit about what makes some of the deep RL things work, right? Since you guys have not been asking me too many questions or anything, I'm going too fast, so I might stop early. I don't know how that works. Anyway, but this part should look very familiar to you, right? From at least from what you did in last class, if not from earlier, right? So basically, have the error function. I take the gradient of the error function with respect to the weights, and I am doing gradient descent.